Hey everybody, we are here on location doing a video in a different room, so if you see things that look different or if things sound different, then that's why. We are going to go ahead and continue taking a look at factors which affect the speed that a reaction takes place. So the next one is the temperature. When it gets hotter, okay, it's going to affect the frequency and the effectiveness of our collisions, okay? So basically what's happening, you make it hotter, particles move faster. When the particles move faster, when they do collide, okay, remember way back here, it said in order for a reaction to occur, they have to collide with enough energy and in the right orientation, okay? If they're going faster, then the likelihood of them colliding with enough energy increases. Okay, so that means that when you increase the kinetic energy, there's more movement, more collisions, more energy, and thus a greater chance of reaching the activation energy. Boom, temperature. Next, we have pressure. If you increase the pressure of a gas, okay, now this is only going to happen if you're dealing with a gas. If you increase the pressure, it's going to decrease the volume occupied. Okay, so think about this room that we're in here. Okay, look at this room. Okay, if you've got a bunch of people in this room and everybody's walking around, and then you cut the room in half and people are still walking around, there's a greater chance for those people to collide with each other. So that is the idea behind pressure. Okay, you decrease the volume, you decrease the amount of space that the particles have to move, and then they are much more likely to collide with enough energy and all that stuff, and you have a greater chance of a reaction taking place. It says, so an increase in pressure means an increase in rate, but only if our reactants are gases. Next, we have surface area. So if you increase the surface area, there's more spots where the reaction can take place. I use the big giant salt crystal idea when we're in solutions about, well, how long would it take for, if you've got a big giant square piece of salt, how long is it going to take for the piece of salt way in the middle, that last little formula unit way in the middle, when is that piece going to dissolve? Well, when everything else around it dissolves, okay? Same thing with reactions, okay? If you've got a big giant piece of zinc and you drop that big giant piece of zinc into a swimming pool full of hydrochloric acid, when is that last atom of zinc that's in the dead center of that block going to react? When all the other stuff around it has reacted. Now, if you want to make the zinc react faster with the hydrochloric acid, all you have to do is put it in powder form, okay? The same mass as the cube, just put it in powder form, and then it's going to all react at the same time. Why? Because you have a greater surface area. You have more spots for the hydrochloric acid to be able to touch the zinc. So if you increase the surface area, you're going to increase the number of collisions, which will increase the rate of your reaction. Next, if we add a catalyst. A catalyst, what's a catalyst? Well, a catalyst is anything that can lower the activation energy. What's the activation energy? Well, when we go back up here, we see this the little hill that you have to climb, okay? When you climb this hill and you get up to the activated complex, the amount of energy that's associated with that is your activation energy. All a catalyst is going to do is it's going to grab that hill and it's going to pull it down, okay? It's going to lower the activation energy, okay? So here is your reactants, here's your products, okay? Normal activated complex, or your normal activation energy, is this amount. What a catalyst is going to do is it's going to drop that down. So now you've got particles which are colliding, but since you've got the catalyst in place, it's going to make it to where you're going to have more particles which collide with enough energy to where your reaction is going to be able to go much faster. Let's see here, concentration. Let's think about it. Let's go back to our room that we're in right here, okay? If I have, let's say I've got 20 people walking around this room, okay? The room wouldn't be very concentrated, right? You've got some people walking around the room, blah, 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 okay? Let's say I want to increase the concentration of the room, okay? And now I'm going to get 150 people in the room walking around. You've got a much greater chance of somebody running into somebody else. Same thing with the concentration of chemicals, okay? If you increase the concentration of your reactants, you're putting more stuff into a smaller area, so you're increasing your molarity. If you do that, you're going to increase your number of collisions, and thus you are going to increase the rate of your reaction. Now, it says an increase in concentration of one or both reactants increases the reaction rate, but just exactly how much increase there will be is determined by the rate law. Now, we're going to look at the rate law in a little bit. Okay, don't worry too much about it right now, but we're going to get there. So let's summarize the things which can impact the rate of a reaction. Number one, if you have a double replacement reaction, it's not a redox reaction, so it's going to occur very quickly. You're not having to switch around your electrons. They are just going to, everybody's just going to do a little switch-a-do, and then reaction takes place. Okay, super fast. Single replacement synthesis and decomp reactions react much slower because they are redox reactions. They have to change their charge. Temperature, increase the temperature, increase the reaction rate, because the particles are going faster, so when they collide, they're going to collide with more energy. Increase the pressure, increase the reaction rate. Why? Because when you increase the pressure, you decrease the volume, thus making it to where you're going to have more collisions. Remember, that one only works for gases. If you increase the surface area, you're going to increase the reaction rate, and if you add a catalyst, you're also going to increase the reaction rate because you've lowered the activation energy. Okay, you've made it to where you can have more effective collisions because now you're going to, when things collide, they're theoretically going to collide with at least enough energy to get up the shorter hill. Lastly, if you increase the concentration, you're going to increase the reaction rate as well because you've stuffed more stuff into your reactants, so now there's a greater chance for a collision to occur. Next thing we're going to look at later on is the rate law expressions. We're going to check those out in the next video though, so I hope you have a wonderful day.